Okay, hi everyone, welcome back to this video series on cryptocurrency. Counterparty. Counterparty is a protocol layer built on top of Bitcoin. The Counterparty protocol, similar to colored coins, offers the ability to create and trade virtual assets and token. In addition, Counterparty offers a decentralized exchange for assets. Counterparty is also implementing smart contracts based on the Ethereum virtual machine EVM, like the colored coins protocol. Counterparty embeds metadata in Bitcoin transactions using the return OP code or one of n multi-signature addresses that encode metadata in the place of public keys. Using these mechanisms, Counterparty implements a protocol layer encoded in Bitcoin transactions. The additional protocol layer can be interpreted by applications that are counterparty aware, such as wallets and blockchain explorers, or any application built using the Counterparty libraries. Counterparty can be used as a platform for other applications and services in turn. For example, Tokenly is a platform built on top of Counterparty that allows content creators, artists, companies to issue tokens that express digital ownership and can be used to rent, access, trade and shop for content, products and services. Other applications leveraging Counterparty includes Spell of Genesis and Grid computing protocols, Folding Coin. Let's get back to in a second, just bear with me. Okay, payment channels and state channels. Payment channels are a trustless mechanism for exchanging Bitcoin transactions between two parties outside of the Bitcoin blockchain. These transactions, which would be valid if settled on the Bitcoin blockchain, are held off-chain instead, acting as promissory notes for eventual batch settlement. Because the transactions are not settled, they can be exchanged without the usual settlement latency, allowing extremely high transaction throughput, low sub-millisecond latency and fine Satoshi level granularity. Actually, the term channel is a metaphor. State channels are virtual constructs represented by the exchange of state between two parties outside the blockchain. There are no channels per se, and the underlying data transport mechanism is not the channel. We use the term channel to represent the relationship and shared between two parties outside the blockchain. To further explain this concept, think of a TCP stream. From the perspective of high-level protocols, it is a socket connecting two applications across the internet. But if you look at the network traffic, a TCP stream is just a virtual channel over IP packets. Each endpoint of the TCP stream sequences and assembles IP packets to create the illusion of a stream of bytes. Underneath, it's all disconnected packets. Similarly, a payment channel is just a series of transactions. If properly sequenced and connected, they create redeemable obligations that you can trust, even though you don't trust the other side of the channel. In this section, we'll look at various forms of payment channels. First, we will examine the mechanisms used to construct a one-way unidirectional payment channel for a metered micropayment service such as streaming video. Then we will expand on the mechanism and introduce bi-directional payment channels. Finally, we will look at how bi-directional channels can be connected end-to-end to form multi-hop channels in a routed network. First proposed under the name Lightning Network, payment channels are part of the broader concept of a state channel, which represents an off-chain alternate state secured by eventual settlement in a blockchain. A payment channel is a state channel where the state being altered is the balance of a virtual currency. State channels, basic concepts of terminology. A state channel is established between two parties through a transaction that locks a shared state on the blockchain. This is called the funding transaction or anchor transaction. This single transaction must be transmitted to the network and mined to establish the channel. In the example of a payment channel, the locked state is the initial balance in currency of the channel. The two parties then exchange signed transactions called commitment transactions that alter the initial state. These transactions are valid transactions in that they could be submitted for settlement by either party, but instead are held off-chain by each party sending the channel closure. State updates can be created as fast as each party can create, sign and transmit a transaction to the other party. In practice, this means that thousands of transactions per second can be exchanged. When exchanging commitment transactions, these two parties are also invalid to previous states, so that the most up-to-date commitment transaction is always the only one that can be redeemed. This prevents either party from cheating by unilaterally closing the channel with an expired prior state that is more favourable to them than the current state. We will examine the various mechanisms that can be used to invalidate prior state in the rest of this chapter. Finally, the channel can be closed either cooperatively by submitting a final settlement transaction to the blockchain, or unilaterally by either party submitting the last commitment transaction to the blockchain. A unilateral close option is needed in case one of the parties unexpectedly disconnects. The settlement transaction represents the final state of the channel and is settled on the blockchain. In the entire lifetime of the channel, only two transactions need to be submitted for mining on the blockchain: the funding and the settlement transactions. In between these two states, the two parties can exchange any number of commitment transactions that are never seen by anyone else nor submitted to the blockchain. In the entire lifetime of the channel, only two transactions need to be submitted for mining on the blockchain: the funding and settlement transactions. In between these two states, the two parties can exchange any number of commitment transactions that are never seen by anyone else nor submitted to the blockchain. Figure 12.4 illustrates a payment channel between Bob and Alice, showing the funding, commitment and settlement transactions. Figure 12.4 illustrates a payment channel between Bob and Alice, showing the funding and commitment and settlement transactions, as I've just said. So here you go. Simple payment channel example. To explain state channels, we have to start with a very simple example. We demonstrate a one-way channel, meaning that the value is flowing in one direction only. We will also start with the naive assumption that no one is trying to cheat, to keep things simple. Once we have a basic channel idea explained, we will then look at what it takes to make it trustless so that neither party can cheat, even if they are trying to. For this example, we'll assume two participants, Emma and Fabian. Fabian offers a video streaming service that is billed by the second using the micro payment channel. Fabian charges 0.01 millibit, 0.00001 BTC per second of video, equivalent to 36 millibits 0.036 BTC per hour of video. Emma is a user who purchases this streaming video service from Fabian. Figure 12.5 shows Emma buying the video streaming service from Fabian using a payment channel. In this example, Fabian and Emma are using special software that handles both the payment channel and the video streaming. Emma is running the software in her browser. Fabian is running it on a server. The software includes basic Bitcoin wallet functionality and create and sign Bitcoin transaction. Both the concept and the term payment channel are completely hidden from the users. What they see is a video that is paid for by the second. To set up a payment channel, Emma and Fabian establish a 2 of 2 multi-signature address, with each of them holding one of the keys. From Emma's perspective, the software in her browser presents a QR code with a P2SH address starting with 3 and asks her to submit a deposit for up to 1 hour of video. The address is then funded by Emma. Emma's transaction paying to the multi-signature address is the funding or anchor transaction for the payment channel. For this example, let's say that Emma funds the channel with 36 millibits 0.036 BTC. This will allow Emma to consume up to 1 hour of streaming video. The funding transaction in this case sets the maximum amount that can be transmitted in this channel, setting the channel capacity. The funding transaction consumes one or more inputs from Emma's wallet, sourcing the funds. It creates one output with a value of 36 millibits paid to the multi-signature 2 of 2 address controlled jointly by Emma and Fabian. It may have additional outputs for change back to Emma's wallet. Once the funding transaction is confirmed, Emma can start streaming video. Emma's software creates and signs a commitment transaction that changes the channel balance to credit to 0.01 millibit to Fabian's address and refund 35.99 millibits back to Emma. The transaction signed by Emma consumes the 36 millibits output created by the funding transaction and creates 2 outputs, one for her refund and the other for Fabian's payment. The transaction is only partially signed. It requires 2 signatures, 2 of 2, but only has Emma's signature. When Fabian's server receives this transaction, it adds the second signature for the 2 of 2 input and returns it to Emma together with 1 second worth of video. Now both parties have fully signed commitment transaction that either can redeem, representing correct up-to-date balance of the channel. Neither party broadcasts this transaction to the network. In the next round, Emma's software creates and signs another commitment transaction, commitment #2, that consumes the same 2 of 2 output from the funding transaction. The second commitment transaction allocates 1 output of 0.2 millibits to Fabian's address and 1 output of 35.98 millibits back to Emma's address. This new transaction is payment for 2 cumulative seconds of video. Fabian's software signs and returns second commitment transaction together with another second of video. In this way, Emma's software continues to send commitment transactions to Fabian's server in exchange for streaming video. The balance of the channel gradually accumulates in favor of Fabian, and Emma consumes more seconds of video. Let's say Emma watches 600 seconds, 10 minutes of video, creating and signing 600 commitment transactions. The last commitment transaction #600 will have 2 outputs, splitting the balance of the channel, 6 millibits to Fabian and 30 millibits to Emma. Finally, Emma clicks stop to stop streaming video. Either Fabian or Emma can now transmit the final state transaction for settlement streaming video. Either Fabian or Emma can now transmit the final transaction for settlement. This last transaction in the settlement transaction, and pays Fabian for all the video Emma consumed, refunding the remainder of the funding transaction to Emma. Figure 12.6 shows the channel between Emma and Fabian and the commitment transactions that update the balance of the channel. In the end, only 2 transactions are recorded on the blockchain: the funding transaction that established the channel and a settlement transaction that allocated the final balance correctly between the 2 participants. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.